June 2025. This month, NASA's James Webb Space Telescope made a historic discovery. And this discovery will bring a major change in the history of space science in the future. A discovery has been made that scientists have been waiting for over 30 years. The James Webb Space Telescope, the most advanced telescope humans have ever built, has now achieved something that was never possible before. Imagine, among billions of stars, around a star like our Sun, there is a planet that is now directly visible. And this discovery was not accidental. It is the result of a planned mission that is going to give humanity a completely new perspective on exoplanets. So stay tuned, because at the end of this video, I'm going to tell you a mind-blowing fact. So let's begin today's video. Welcome to Quantum Quarks. Friends, in June 2025, the James Webb Space Telescope added a golden chapter to the history of space exploration. Now, you might be wondering what's different about this. After all, we've discovered and studied exoplanets before, but this discovery is very different from all of those. Friends, until now, we used various methods to find planets, which we will understand later, but there's something new about this discovery. For the first time, we have captured a direct image of an exoplanet. But wait, this is not just a routine discovery. This achievement is the result of over 30 years of technological advancement, and its impact will be so deep that it will change the way we discover planets or alien life. Now, before I tell you how revolutionary this discovery is, let me take you on a short journey. Till the 1990s, exoplanets existed only in science fiction. Scientists theoretically knew that there should be many stars and planets like our solar system, but there was no proof. In 1995, 51 Pegasi b was discovered, the first confirmed exoplanet orbiting a sun-like star. Michel Mayor and Didier Queloz made a discovery in 1995 that shook the world of astronomy. They detected a planet outside our solar system using the radial velocity method. But this is an indirect method because it doesn't allow us to see the planet directly. So, what is the radial velocity method? Radial velocity is a technique in which we measure a star's light spectrum with extremely sensitive instruments. When a planet orbits its star, the planet's gravitational pull slightly tugs the star. This causes the star to make a small, wobbling motion, meaning it moves a little back and forth. Because of this movement, there's a tiny Doppler shift in the star's light. When the star moves towards us, its light shifts slightly bluer. When the star moves away from us, its light shifts slightly redder. By measuring this shift, we can figure out if there's a planet around the star, how massive it is, and how large its orbit might be. Radial velocity observations have detected many planets, such as 51 Pegasi b, Michel Mayor and Didier Queloz's first discovery, a hot Jupiter orbiting very close to its star. This was the first confirmed exoplanet found around a sun-like star. Gliese 581c, famous for being in its star's habitable zone, with strong possibilities for liquid water, which could mean the existence of alien life. HD 29458b, Osiris, the first planet whose atmosphere was detected, and it was also confirmed through radial velocity. Proxima Centauri b, a planet in the habitable zone of the closest star to our solar system. Then came a new method we call the transit method. With the help of the Kepler Space Telescope, we nearly perfected this technique. The principle of this method is simple, but its execution requires extremely precise and careful observations. Friends, when a planet passes in front of its star, a process we call a transit, the star's brightness drops slightly. Imagine a tiny insect flying in front of a light bulb. The bulb stays in place, but for a moment, when the insect crosses in front of it, the light dims just a little. Astronomers measure this drop in brightness to detect planets. Using this method, the Kepler telescope detected over 4,000 exoplanets, and many of these are potentially habitable. Some famous examples include TRAPPIST-1 system, a single star with 7 Earth-sized planets, 3 of which are in the habitable zone. Kepler 452b, often called Earth's older cousin, similar in size to Earth and located in the habitable zone. Kepler 186f, the first Earth-sized planet found in the habitable zone. But this method also detects planets indirectly. We don't take a picture of the planet. We only estimate its presence by measuring the small dip in light when it passes in front of its star. Now let's talk about direct imaging, which means actually photographing an exoplanet. This is the most difficult method of all. The question is, why? Imagine trying to take a photo of a candle that's burning right next to a lighthouse from 200 light years away. The lighthouse, representing the star, is billions of times brighter than the candle, which represents the planet. On top of that, Earth's atmosphere, light pollution, and other radio wave turbulence make things worse. For ground-based telescopes, this is almost impossible. Still, there have been a few successful attempts, such as with the HR 8799 system and Beta Pictoris b. But these were rare cases, and the planets were massive and young, meaning they were hot and bright enough to be visible. But now, the James Webb Space Telescope has completely changed the game. December 2021, we humans launched the most powerful technological marvel ever built, the James Webb Space Telescope, and by 2022, it became operational. NASA scientists, with nearly 30 years of hard work and dedication, made this once impossible technological wonder a reality. It is considered the successor to the Hubble Space Telescope, which itself was a remarkable feat of technology. But JWST is about 100 times more powerful than Hubble in terms of capabilities. Its 6.5-meter primary mirror has a light-collecting area 6.25 times larger than Hubble's. JWST uses infrared light, which is perfect for studying cooler objects like planets. It is positioned at the L2 Lagrange point, about 1.5 million kilometers from Earth, where it operates in a completely stable, interference-free environment. James Webb has already done incredible work in the field of exoplanets, studied the atmosphere of WASP 96b, and detected water vapor, observed K2-18b to study cloud formations and weather patterns, measured day-night temperature differences on several exoplanets with extreme precision and accuracy. When a planet passes in front of its star, JWST can study the starlight filtering through its atmosphere to reveal its chemical composition. But direct imaging, that's a whole new level of achievement. TWA7 is a very young star, only about 10 million years old. Compare that to our sun, which has been shining for 4.6 billion years. TWA7 is still a cosmic baby. It belongs to a special stellar family, the TW Hydrae Association. Imagine dozens of stars being born in the same place, a kind of interstellar nursery. This nursery lies hidden about 111 light years from Earth, inside the Hydra constellation. In terms of mass, it's slightly smaller than our sun, around 0.8 solar masses. Its surface temperature is about 4,000 Kelvin, a bit cooler than the sun's 15,800 Kelvin. But cooler doesn't mean dim. Young stars like TWA7 still radiate leftover heat from their formation, making them shine brightly in infrared light, which is exactly why their planets can be captured through direct imaging. And orbiting this young star, scientists have discovered a gas giant named TWA7b. It has a mass roughly equal to Saturn, around 95 Earth masses, and orbits 15 to 20 AU from its star, about the same distance Saturn orbits the Sun in our solar system. Its temperature? Around 1,000 Kelvin, 727 degrees, still glowing from the heat of its youth. At only 10 million years old, it's like a freshly baked planet, radiating a red-hot glow. From its composition, scientists are confident it's a gas giant, possibly with a hidden rocky core. And it was the perfect target for the Webb telescope. To confirm this discovery, the James Webb Space Telescope followed a carefully planned strategy. Multiple observations were made on different dates. Each time, the planet's position shifted slightly, a strong sign it wasn't a background star, but was orbiting its host star. Infrared spectral analysis was performed. Webb dissected the planet's light to capture atmospheric signatures, clues pointing to molecules like water vapor, methane, and carbon monoxide. Contamination checks were run to ensure the signal wasn't from a background galaxy, star, or imaging artifact. When all the analysis was done, scientists had a 99.99% confidence level. Yes, this was a real exoplanet. Total observation time? About 10 hours, spread over multiple sessions. Its impact? A permanent chapter in the history of space science. Why is this discovery revolutionary? We can study a planet's properties directly without interference from its star. From its direct light, we can extract detailed atmospheric compositions, which in the future might even reveal signs of alien life. Potentially, we could detect weather systems, giving us deeper insight into conditions critical for the creation of life. This will help us search for biosignatures, clues that could tell us more about how life forms emerge. All of this proves that the James Webb Space Telescope is fully capable of direct imaging. Now, here's the most exciting part of this discovery, the one I promised you at the start of the video. The detection of TWA-7b is not just another direct exoplanet discovery by James Webb. It's actually a stepping stone towards something much bigger. Scientists have analyzed this planet's atmospheric data and found some unexpected chemical signatures. There are hints of complex organic molecules, methane, carbon monoxide, and some unidentified spectral lines that could indicate advanced chemistry. But this isn't even the most interesting part. The real shocker: this young planetary system also contains a debris disk, suggesting the presence of an asteroid belt or a comet cloud. And when scientists analyzed this debris disk, they found water ice signatures and complex hydrocarbons. In other words, this 10 million-year-old system already has the chemistry to create the building blocks of life. And here's the mind-blowing part. Computer simulations show that this system might be forming rocky planets right now, the kind James Webb can't detect yet because of the star's brightness. So we could be witnessing a planetary system evolving in real time, one that billions of years from now could look like our solar system. Friends, this discovery literally opens up a new era in exoplanet science. Webb has proven that direct imaging is not only possible, but incredibly informative. TWA-7b is just the beginning. There are hundreds of young planetary systems Webb could target next. And the most exciting part? As technology advances, we might one day directly image Earth-like planets and search their atmospheres for biosignatures. If you found this video informative, please like and share it. Comment below, do you think we'll be able to directly image Earth-like exoplanets within the next 10 years? For more such fascinating videos, subscribe to Quantum Quarks so you can stay updated on the latest discoveries and mind-blowing facts. Thanks for watching, and stay tuned.